In Module 5, Lesson 13, we're going to continue practicing with the formulas for volume. In our first example, we're asked to find the volume of a cube with side lengths of 2 1/4 centimeters. So since it is a cube, that means that each of the sides has the same measurement. We do 2 1/4 times 2 1/4 times 2 1/4. And we find the volume of that cube to be 729/64 cubic centimeters. And we don't always have to change our improper fractions back to mixed numbers, especially if we are working with fractions throughout the problem. But if we do, we get 11 25/64. Next, we need to determine the volume of a rectangular prism with a base area of 7/12 square feet and a height of 1/3 feet. So in looking back at volume, volume equals length times width times height, but another form of that is area of the base times height. And so when they tell us it's a rectangular prism with a base area of 7/12 feet, we know that's this part, and then we multiply that times the height. So that volume then is 7/12 times 1/3, which is 736 cubic feet. In exercise 1, we're asked to use the rectangular prism shown in the picture to answer the next set of questions. First, we need to determine the volume of the prism. Now, they're telling us that the area of the base is 13/2 square feet. Area, and we know this is the base. So we're going to multiply the area of the base times height. Which would give us 65/6 or 10 5/6 cubic feet. Then we're asked to determine the area of the prism if the height of the prism was doubled. So that would give us 13/2 times 10/3, because if we doubled 5/3, that would be 2 times 5/3, or 10/3. And that'll be 136, or 21 2/3 cubic feet. Now, when we look at the two volumes, 65/6 and then 136, what we should notice is that the volume in part B is 2 times the volume in part A. So when we doubled the height, we doubled the volume as well. So let's go ahead and complete the table showing those same relationships. If we have 5/3, this was our original volume. Our volume was 65/6. If the height is doubled to 10/3, our volume was doubled to 130/6. Notice the denominators are not changing. If our height triples from 5/3 to 15/3, then our volume would triple as well to 195/6. And then if our volume quadruples, we would have 266. So our volume tripled when the height was tripled, and our volume quadrupled when the height. So we could say then that when the base area stays constant and only the height changes, so when the height is multiplied by a number, the original volume will be multiplied by the same number. It's a proportional relationship. In question 2, we're going to write some algebraic formulas to represent what we have been doing mathematically. If A represents the area of the base and H represents the height, we need to write an expression that represents the volume. So our area of the base, A, times H, would be volume, A times H. If we doubled the height, the new height would be 2H, because doubling means multiplying by 2. And then representing the volume with the doubled height would be 2AH, because multiplication is commutative, so we can do it in any order. We normally put the number in front of the variables. And then we could write something like 2 times AH in parentheses, just showing that it is doubling the volume. In question 3, we're going to use this cube to answer the questions. Remember, a cube has the same dimensions all the way around. So when they give us one measurement, that measurement applies to all of the sides. The volume of this cube then would be 3 times 3 times 3, which is 27 cubic meters. Then we're asked to determine the volume of a cube whose side lengths are half as long as these side lengths. So half of 1/3 would be 1 1/2. So the volume of a cube whose side lengths are half as long would be 27/8, because now we have a 3 in the numerator, a 2 in the denominator, essentially. Same units. Next, we'll determine the volume if the side lengths are 1/4 as long as the original cube side lengths. So that would be 3/4 for each side length, because 3 times 1/4 is 3/4. And that would leave us at 27/64 cubic meters. And then determine the volume if the side lengths are 1/6 as long. So we would have then So we would have 3/6 and this probably will set off a memory in some of you. 3/6 times 3/6 times 3/6, but 3/6 is equivalent to 1/2. So it's 27/216, but when we simplify, it's 1/8 cubic meters. So when we explain the relationship between the side lengths and the volumes of the cubes, we can say that if each of the sides are changed by the same fractional amount of the original, then the volume of the new figure will be 1 over a to the 3rd power, where a represents whatever the change of those sides for that cube is. Okay, just like when we changed by half as long, and when we changed by 1/4, and we changed by 1/6, 1 over a cubed is what we end up with for our original amount. For example, if the sides are 1/2 as long, then the volume will be 1/8 as much as it was. We're going to check to see if this relationship is true for a rectangular prism, not just a cube. So the volume of the original prism is 9 by 2 by 3, which is 54 cubic feet. And then if all the sides are half as long as the original lengths, that would be 9/2 times 2/2 times 3/2, which would be 54/8. And that simplifies to 27/4. And then if all the sides are 1/3 as long, we would have 9/3 times 2/3 times 3/3, which would be 54/27, or 2 cubic feet. And so yes, the relationship that was found with the cubes still holds true with this rectangular prism. So then we'll translate that into an expression. And if E represents the edge length of the cube, the volume of that cube then would be E to the 3rd power. If we divide the edge lengths by 3, then we would have 1/3 E, or E divided by 3. And so the volume of the cube with 1/3 the edge length then would be 1/3 E to the 3rd power, or E divided by 3 to the 3rd power.